And we end at 3 or around 3, right?
Yeah, in about an hour. Yeah. Welcome, everyone. It's my pleasure to host this last colloquium of complexity. And we're delighted to have Tina Eliassi-Rad from Northeastern University. She's professor of computer science and also faculty member at the Network Science Institute and Institute for Experiential AI. And her work has had broad impact in several areas. I don't want to take time from her detailing her CV, but it's very impressive. So she will speak about machine learning. So please, Tina.
Thank you so much, Carlos, for inviting me for the nice introduction. Let me share my screen here. So thanks again. It's a privilege to be able to speak with you all about a project I have called Just Machine Learning. So what is machine learning? I know there's a lot of hype around it these days. Arthur Samuel coined the phrase machine learning way back in 1959 as the field of study that gives computers the ability to learn without being explicitly programmed. And what you're seeing here is Arthur Samuel sitting next to the very first machine learning program, which was his checkers playing program. And his program wasn't really generalizing or learning the way we think of now. It basically memorized every state of the game with a terminal reward of having been in that state. So I usually start with this slide in that machine learning has been around for a very long time. And now, of course, there's this hype about it. So what are components of a machine learning system? There's a task, obviously. Usually it's a prediction task, and there's lots of data. In fact, part of all the buzz around AI is all the data that people generate online, for example. So in addition to the task and the data, then there is some model. For example, here I'm showing you a feed-forward neural network with 3 hidden layers. So some mathematical representation that you believe this would represent your data well. Now, of course, you would need to learn parameters of that model. So to do that, so here would be the weights on the edges, you define a loss function, and then you need an optimization algorithm. For example, for a artificial neural network, it would be something like a back propagation. And so this is all the components of a machine learning system. So let's go through them and look at some of the parts that we have to approach with caution. I'm sure you've heard a lot about data and the issues around data. So as I was saying, the excitement around machine learning is in part due to all the data that we're generating, we the public are generating. And that data is then fed to these machine learning models to, for example, do image recognition, speech translation, text generation. And what is happening is that data, as for example, this paper, recent paper shows, is full of misogyny, pornography, stereotypes, etc. Even when they curate it, you still have these kinds of issues because to learn those very big models with billions of parameters, you need a lot of data. And so you can't really go through them to curate them. And so there is this issue of the societal biases that we have existing in these data sets. So what could you do, right? Timnit Gebru, who was the co-lead for ethical AI at Google, who was fired by Google last year, and her colleagues have a paper. This paper actually came out in 2019, but was just published, and it's titled Data Sheets for Data Sets. So what this says is that when you have a data set, in a way, you should have a long-form birth certificate for it. You should have a motivation for why that data was collected, how it was composed, what was the collection process, how did you pre-process it, clean it, label it, what are its uses, how are you distributing it, and how you're maintaining it. This is an extremely useful thing to have for each data set that are being used, especially in these kinds of high stakes situations. Now, I have framed this in part that, oh, we are generating all this data, and of course in our societies there are these biases, and that those biases exist in this data. But if we look at even data that is not social data, like Twitter data or Facebook data or Google data, we still see these kinds of social issues in the data that we're getting that then we're giving to our machine learning models. So during the COVID pandemic, everybody was very interested in these oximeters, where you're seeing it in this woman's hand, where it will tell you what is the oxygen saturation in your blood. And there was this big story last year around this time that these oximeters that you can buy in pharmacies don't do well on darker skinned people. And there was a big brouhaha about it. And this guy wrote a little survey on it and said, oh, we knew this back in 2005 and 2007. And of course, nobody did anything to it. So I dug a little bit deeper into this. I went and looked at that 2007 paper, and I saw that that 2007 paper was citing a paper back in 1992 that showed that these oximeters don't do well on darker skinned people. And that 1992 paper was citing a 1990 paper where we knew this was not good. And that 1990 paper was citing a 1987 paper that these oximeter data are not good on darker skinned people. And in fact, you can even follow this back to 1950s, where they were trying to measure oxygen saturation in the blood through the ear, and they had noticed that it doesn't work on darker skinned people. Now, imagine all the data that has been collected throughout the decades that are going into the machine learning models to predict, for example, who should be hospitalized and who should not be hospitalized. Or if you're a darker skinned person, you're using this oximeter information and you think the oximeter is working for you, but it's not working for you, right? So the issues around data are not just social data and the societal biases that we see in the social data, but also in other types of data that are collected, whether in medicine or in criminal justice or other kinds of fields like hiring or school assignment. So working with my colleague, Deborah Ramirez, who's a lawyer at Northeastern University, she asked me, can we generate aspirational data? And I'm like, well, what is an aspirational data? And Debbie said, aspirational data is synthetic data from an ideally fair circumstance. So if you can imagine living in a utopia, right, where that utopia is completely fair, we would like to see how we can generate that kind of data. And then I'll tell you what, for example, you could do with that kind of data. And the key is ideally fair circumstances. So we took this task on, and we looked at John Rawls's well-ordered society. So John Rawls was a very famous political philosopher, and he wrote this book, Theory of Justice, back in the 70s. And he said a society is well-ordered when it advances the good of its members and is effectively regulated by a public conception of justice. And in particular, if you look at John Rawls's work, he has two principles, the difference principle and the fair equality of opportunity principle. And we looked at this fair equality of opportunity principle. So this is basically where our ideally fair circumstances come from. So fair equality of opportunity governs the allocation of advantageous positions, such as high-paying jobs in society. Luckily, fair equality of opportunity can be formalized as a conditional independence, which says that the probability of securing a good job should be independent of variables such as race, so these kinds of protected variables, race, gender, etc., given some justified variables like your talent, right? So the probability of you getting a position at a university should be independent of whether you're Hispanic or not, given your talent. Your talent is the only thing that has to come into play. That's what John Rawls believed in an idealistically fair society. And so you could represent it as a conditional independence. So now we could formalize it. Many of these fairness measures, and I'll talk about them, they don't play well together in that there's an impossibility result around them. But for now, this is what we're assuming is fair. So then we ask this question, given an unfair, in the sense that Rawls says for the fair equality of opportunity, given an unfair outcome, and the capacity to alter some of the decision-making processes, so some of the policies, can one satisfy FEO? And so our answer was yes. We developed a system called Rawls-Net, which is a system that will alter the parameters of a Bayesian network in order to satisfy fair equality opportunity. And this paper was with my students, David Liu, Zohair Shafi, my postdoc, Will Fleischer, and my colleague at Amherst College, Scott Alfeld, and was published at last year's AI Ethics and Society. So what is Rawls-Net? So Rawls-Net has three components. You give me a data, I learn a Bayesian network, right? The direct acyclic graph. I then determine whether your application is actually relevant to FEO. FEO is very narrow. It just really is about these kinds of advantageous positions in society. And then what Rawls-Net does is it updates the parameters of the Bayesian network in order to satisfy this fair equality opportunity. If there are constraints, for example, UNAM can only take so many students, can admit so many students, it will update the parameters approximately to satisfy fair equality of opportunity. So here's an example. It's college admissions. What you're looking at is the Bayesian network, and it's a very simple Bayesian network. Basically, your test score depends on your talent and your socioeconomic status. This makes sense, right? So if you come from a high socioeconomic status, perhaps you can get a private tutor, and that private tutor will improve your test exam by working with her or him. Then, depending on your socioeconomic status and your test score, that's where, like, colleges, whether they will admit you or not. We know, for example, in America, there's all these legacy admissions, right? So the socioeconomic status does matter. And then for the job, it depends on which college you go to and your socioeconomic status. So this, even though it's a toy model, it kind of represents what the world is. And what we are interested in is, can we change the parameters for college, the college admissions policy, in order to make it such that when it comes time to make a decision about a job, that satisfies fair equality of opportunity. That really, whether you get a job or not only depends on your talent and not on your social economic status. So you can represent this as an optimization problem. It's a Bayesian network, so you have the DAG, the direct acyclic graph, and then for every node, which is a variable, you learn these conditional probability tables. You can also learn structural equations. For example, you could use a deep network to learn a structural equation, but we're going to put that aside for now. We're just looking at conditional probability tables. So the admission policy is this theta of college, which represents this table, this conditional probability table. And then the optimization problem is, find me values for theta college that will minimize this objective function. And the objective function basically is saying that probability of it giving a job should not depend on the social economic status. That is, given that you have no talent, the probability of giving a job should not matter whether you're coming from a low socioeconomic status or a high socioeconomic status. And inversely, given that you are very talented, again, probability of getting a job should not depend on which socioeconomic status you're coming from. They're subject to, this is just your learning probability, so it should be between 0 and 1. And then there could be some feasibility issues that you need to deal with. So I just went through this. So this was probability of getting a job where you don't have talent should not depend on your socioeconomic standing, and probability of getting a job, given that you're talented, should not depend on your socioeconomic status. And these are the constraints. So in simulations, we can see whether we're actually doing a good job in terms of optimizing that objective function. On the left, what you're seeing is different stages of somebody's life. I know this is kind of boring. So you're born, you test for college, you go to college, you get a job, and that's where our simulation stops. On the y-axis, you're seeing the probabilities. And before we apply our system, these probabilities line up with what we're seeing in society. So if you are not coming from a high socioeconomic status and you're not talented, the probability of getting a job is low, versus if you are coming from just a high socioeconomic status, the probability of getting a job is actually higher than if you were talented. And this is when you have both. You have both high socioeconomic status and you have talent. And we see that after we optimize for fair equality of opportunities through Rawls net, that it doesn't matter whether you come from a high SES, socioeconomic status, as long as you're talented, or talented and come from high socioeconomic, as long as you're talented, you're good, right? So the purple is both, where you have high socioeconomic status and are talented, and blue is just that you're talented. And that's what we wanted to see, that really it's just talent that matters. Now, of course, as I said, colleges, for example, can only admit a certain number of students. And so there could be that there are feasibility constraints. And what we see is that when we do our optimization algorithm, we get the lines closer to where they should be, where again, it's the talent that decides the outcome, as opposed to the socioeconomic status. So what are the uses of like a tool like this, right? So we can generate through this Bayesian network and the parameters that we learn, we can generate this aspirational data that Debbie Ramirez wanted, right? And so we can generate this synthetic data from ideally fair circumstances that satisfy the Rawlsian fair equality opportunity. This can aid the policymakers in their decision-making in terms of, for example, school acceptances. There is a big caveat that you need to really know about distribution of talent, right? So this is where you can't just be in your clean office and ruminate over what's the distribution over talent. You need to go hit the pavement, talk to high school counselors, and really understand about what's the distribution of talent in your society. So this is not one of those things that you can just like get data and then plug it in. That's not how we want you to use it. We want you to use it where you're actually working with the community and you understand what the distribution of talent is. So that was about data. Let's talk about model. So Margaret Mitchell, which was the other co-lead of the Google Ethical AI team, who was fired about 11 months ago with Timnit, etc., they had a paper similar to the data sheets for data sets about model cards for model reporting, where again, if you are going to learn a model, you need to have a document associated with it, which details the model, how it should be used, what are its factors, what are some of its metrics, what was it trained on, how was it evaluated, ethical consideration, etc. And part of this is awesome and part of it is because, for example, you show some quantitative analysis, but just looking at this, you're like, oh, I shouldn't use this model on old males. The false discovery rate on old males is very large. And so in a way, machine learning systems should be treated like prescription drugs, right? Because they do not work equally across the population. And so what we did was we took then the data from RawlsNet and we said, okay, here's a aspirational data. Here's a fair distribution. Am I good now? If I just send it to a machine learning model, will the machine learning model learn that fair data distribution? And what we saw was that it's not as simple. That just because your data distribution is fair, you can't just say, okay, you know, my data is fair, my society is perfect, I'm just going to run it through a machine learning model. It's all math anyways. It will all come out well at the end. And so we looked at Bayesian networks, we looked at maximum likelihood estimation, and we saw that you cannot sit back and just say my data is fair, so I'm going to be fine. It depends on lots of different factors like the faithfulness of the learned joint distribution, the correctness of the learned joint distribution, the correctness of the Bayesian network structure that you learned, et cetera, et cetera. So I talked about the data and the model. I want to talk a little bit about the task here. So a lot of the tasks that have been, that machine learning people really like and are being used in these high stakes situations are prediction tasks, specifically risk assessment tasks. Risk assessment is very easy for machine learning people because it just sorts you into buckets. It's just sorting, nothing else. This is a paper that was published in Science in 2019, which it wanted to predict healthcare costs. Well, actually, it wanted to predict illness. Sorry, it wanted to predict illness, but it could not. So what it did was it was predicting healthcare costs. And of course, healthcare costs are very much tied to your socioeconomic status, to your race, to your gender, etc. So we will come back to that problem in a little bit. So let's talk a little bit about this risk assessment. It's extremely popular, as I mentioned, in part because, as I said, it's a low-hanging fruit for machine learning people. It's just sorting people into the different buckets. Also, the human decision maker that's going to be using your machine learning algorithm can understand the output really well, in part because the risk assessment software oftentimes do not report any kind of probabilities of how certain, for example, the algorithm is in terms of putting you in a different risk score. Basically, it's like, well, if I'm figuring out about bail or pretrial disposition and somebody's risk score is high, like 7, 8, whatever, then they just don't go, you don't give them bail, right? And of course, that's, you should not be using it that way, but unfortunately, there are private software that are being used in some states in America that do that. So what are the issues with this risk assessment task? It's because there are these impossibility results, hence mission impossible. So I'm sure you guys know in machine learning, especially in supervised learning, where basically you have rows of data and some kind of a value, target value, whether somebody should get a loan or not. We start from this error matrix or confusion matrix, where you see, well, what was the true condition and what did my machine learning classifier or machine learning algorithm predict, right? So that's basically what it is. So you have your true positives, your true negatives, false positives and false negatives. And from that, you can come up with lots and lots of different measures. For example, accuracy is summing your true positives and your true negatives divided by your total population, et cetera, et cetera. So what happened is in 2016, Cheldakova, who's a professor at Carnegie Mellon University, published a paper that showed the following impossibility result. She said, suppose I have a population and I divide them into two groups that are mutually exclusive. So suppose I take my population and I divide it into females and non-females. And suppose that I have unequal base rates. That is, the probability of my females getting breast cancer is not the same as probability of my non-females getting breast cancer. This seems reasonable as well. And then she said, suppose I want to also have statistical parity. That is, the probability of my classifier or of my machine learning model, the trained machine learning model, predicting that a female has breast cancer is the same. I want that to be the same as the probability of my classifier doing the same for a non-female, that is classifying that a non-female has breast cancer. Then what she showed was that you cannot have these three fairness or statistical parity measures that you would want. You cannot have predictive parity, that is among your females. You can't have the probability of the female having breast cancer, given that your classifier said she has breast cancer, being the same as that probability among your non-females. And you can't have true positive parity, which is the probability of among your females, your classifier saying that the person has breast cancer, given that in fact they have breast cancer, compared to what you have in your non-female population. And the last one, false positive parity, which is the probability among your females that your classifier says somebody has breast cancer, given that they actually don't, will not be equal to the same probability for a non-female. So given these three very reasonable premises, you cannot satisfy all three parities at the same time. And then John Kleinberg et al. That same year said, okay, what I'm going to do is I'm going to get rid of the statistical parity. I'm still going to divide my population into two groups that are mutually exclusive, females and non-females. And I'm also going to assume this unequal base rates, right? My females get more breast cancer. Than the probability of a female getting breast cancer is more than the probability of a non-female. But what Kleinberg et al. Said, I'm going to get rid of statistical parity. Instead, I'm going to assume that I have an imperfect classifier. And if you come up to a classifier or a machine learning model that is perfect, run the other way. And also that I have this non-zero precision. That is, there are cases in which, for example, the probability of a female having breast cancer, given that my classifier says breast cancer, is not zero. Again, he showed that you can't have these three fairness measures at the same time. And then recently, with Feidelson, we showed that you don't even need mutual exclusivity, right? So you can have somebody that's female and non-female, or you can have somebody that's black and white, like Barack Obama. And again, if you have an imperfect classifier or non-zero precision, you can satisfy these three fairness measures. And we showed in the same work that you can even get rid of imperfect classifier and non-zero precision premise and just say that I have regular priors, in that the prior probability that I assign is only extreme for things that are either necessary or impossible. And still, you can have these three parity measures satisfied at the same time. And these are very simple proofs to derive. You can find your own impossibility results. You can download the Mathematica notebook here, or if you want to learn about more impossibility results, just download this PDF. So what has been the fallout with these impossibility results? Computer scientists are very good at bastardizing things because we want them to work. So one of them is just get rid of one of the parities. I can't satisfy all three, I'll get rid of one of them. Or I can say, okay, I can't satisfy all three, but maybe I can put some bounds on satisfying one of them. Now, Deborah Hellman, who's a professor of law at University of Virginia, has been thinking about what these parity measures actually mean in a human term, not in these like probabilistic equation terms. And so she has this great paper that's up on SSRN, where she says predictive parity captures this notion of what you ought to believe, and true positive parity and false positive rate parity capture what you ought to do. And so if you are going to look at just predictive parity, what your algorithm is going to do is it's going to look for these right-making properties. And the right-making properties in our societies are being a white male. And so your algorithm is going to be kinder to the white males than anybody else. And so she argues that if you're actually going to drop one because you can't satisfy all three, that you should drop the predictive parity. Now, at this point, you may say, well, Tina, you have been talking about these kind of group fairnesses. What about individual fairness? And so Cynthia Dwork et al., folks who worked on differential privacy have said, well, okay, why don't we define individual fairness, which is two people that are similar should be treated similarly. And so my postdoc, Will Fleischer, had a paper in the AI Ethics and Society conference last year discussing how there are problems with individual fairness. So just because you and I are treated similarly doesn't mean that it's being fair in the overall picture of society. And of course, there are going to be systematic biases in terms of what is similar, so who's similar to whom, and you're going to be making these kinds of moral judgments about which features are important for which tasks. And then you could also have cases where you can't just compare. So it's incommensurable. You just cannot compare, for example, let's say prestige with higher salary. It just cannot be compared. So then you don't have similarity there. That is commensurable. And so his takeaways is that individual fairness is inadequate as a definition of fairness, and that individual fairness should never be used as a sole means for determining fairness or detecting bias. So now, instead of going through loss function and optimization, I want to pop up and say that one of the things that machine learning people unfortunately never look at is the fact that their machine learning system is being operated within this complex system, right? And so the complex system has disorder, all the good things that you already know and love. It has this nested structure, it has feedback, it has diversity in it, it has modularity, etc. And so we really need to think about our machine learning systems and the issues in terms of data and the model and the task and et cetera, within a complex system. And so recently, with the lead of Claudia Wagner and Marcus Strohmeyer, we had a paper in Nature. This is just a perspective piece in Nature, talking about how do we measure our societies that are now infused with algorithms. So if you think about our societies, such as, for example, dating, right? A lot of people now use these online dating sites, which use algorithms. Those algorithms make dating recommendations that influence your social processes, that then influence whatever the social acceptability is, that then influence the algorithm. So then you go round and round in this kind of feedback. And the same thing happens in terms of economics. So if you go to Amazon, their algorithms will recommend certain products to you that you buy, and that influences the winners, right? It separates the winners from the non-winners. And the same in terms of our politics, right? In terms of, for example, what you see on your news feed, etc. So there's definitely this feedback. And so in that paper, we talk about 3 challenges that we need to target. One is this insufficient quality of measurements. 2 is this complex consequences of mismeasuring. And 3 is the limits of existing social theories, because these social theories were not developed when we had all this data available, and we were living in societies that were infused with algorithms. So just in terms of some key concepts as I go through these challenges, obviously social data is what you know and you contribute to. So data, whether through the digital devices, through the services that you use on your phone or elsewhere, through the infrastructure. The social theories are, like the social capital theory, the strength of weak ties, etc. So explanatory conceptualization of social phenomena. And then there are these kinds of measurement models, which are the theoretical and empirical approaches that will tie high-level social constructs with the observable data. And part of the issue with the measurement models is that we need to be careful and be able to justify why what we are measuring is what we think we are measuring. So going back to the science paper, they thought they were measuring illness, but what the authors of the science paper showed was that they were really measuring healthcare costs, right? And not not illness, and like, oh, this person is more ill, so I should take care of him more. So the first challenge is this insufficient quality of measurements. There are no guidelines, right, and standards in terms of how do you measure things, how do you collect data. Oftentimes, unfortunately, the computational methods fail to make their assumptions explicit and test them. We see this, especially machine learning models have lots of hyperparameters. These are parameters that you do not learn from the data. And oftentimes people do not do model selection. And sometimes the data that you train your algorithm on and the data that you're testing it are coming from different distributions. And so the transfer doesn't go very well. And the data sets that are used oftentimes will basically mitigate the kind of biases that we have in our society. And there's no description or the justification of the data selection. Like every time I've brought up this notion of data sheets for data sets, oftentimes the people who are collecting the data, they're like, oh, this is yet another work that I need to do, right? Which I don't see it as another work that you need to do. It's absolutely necessary that if you're collecting data, that you have some description of it about how it was collected, how it should be used, etc. And so here, some of our solutions are to, if you triangulate your observations from the complex system that you're trying to observe, that should help. you should develop guidelines and practices in terms of how you would collect data. So a few years ago, Google realized that they weren't doing very well at recognizing Black faces. That is, their image recognition system was not doing very well at recognizing Black faces. They hired a subcontractor to collect more Black faces for them, as in images. And that subcontractor went to Atlanta, which is a city in America that has a lot of Black folks there. And that subcontractor was looking for college students and homeless people and would give them each $5, have them sign a consent form, and then take their photos, right? Clearly, that is not ethical. So you need to really develop these guidelines and best practices up front. Challenge number 2 is actually the consequences of mismeasurement, right? So now, if you had gone with what Google had done, your machine learning algorithm will learn that Black people are either homeless or college students, right? And that is obviously not okay. And there's this trade-off in terms of privacy versus transparency. And so, again, what you need to do is you need to be upfront in terms of the values. And this is where Helen Nissenbaum, who is a philosopher and a computer scientist at Cornell Tech, has always been talking about value in technical design. That is, before you start designing a system, you need to say, okay, what are the values? What are the norms that I need for this system? And as LaTanya Sweeney, who's a professor at Harvard, says, if you wait until the very end to think about ethics, it's too late, right? So you need to start at time T0 thinking about, well, what kind of data do I need? Is it ethical for me the way that I want to collect that data? Should I even have that data? How much privacy is lost, et cetera, et cetera. And then challenge number 3 is that basically the social science theories that we have were not developed in terms of, oh, I also have an algorithm that is steering the way the society is going. And what I need to do is pay attention to that and pay attention to the fact that now people can travel all over the place. Well, with COVID, there's some restrictions, but before pandemic, because there was more mobility, the population characteristics were more dynamic. And so you need to have these social technical environments that are adaptive. You can't just be English heavy. You have to be able to address other languages as well and other cultures. And so again, this is part of, we need to come up with new theories that need to take into account both the data and the measurements that we're having, and we need to be transparent throughout the process and talk to the communities that these algorithms are going to be used on. So one of the things that I always ask my colleagues is like, would you want your algorithm to be used on you in these kinds of high stakes social facing environments? And none of them raised their hand. None of them would want their risk assessment software to be used on them. So that makes you think about, what is going on, right? We need to pay more attention to the norms and values and perhaps have professional norms, right? In terms of what machine learning models are being used for what tasks. And then this leads me to another topic that we recently worked on, which is democratic backsliding. I'm sure you're all aware of it, where in the US, among other places, our democratic institutions are not doing as well as they used to do. Here, I'm showing you the Economist Democracy Index, which is composed of, for example, civil liberties, participation of the public, et cetera, et cetera. And one of the things which is interesting, so Waldner and Lust in 2018 published a paper in Journal of Democracy, where, actually, no, I think this was an annual review of political science, where it said that political scientists lack theories to explain backsliding. And that up to now, basically people thought that democracy was a one-way ratchet. That is, when you get democracy, you would not want to go back. But that is not what we're observing, obviously. And this was even before pandemic, much less now. And actually, the Science magazine back in September of 22 had a whole issue on democracy at balance and how now with all the data that we have, we can do these empirical studies on what happens to our citizens' behavior when these kinds of democratic institutions and our trust in them erode. And all of this actually started for me, this work, in thinking about democracy as a complex system and thinking about democratic backsliding as instability in this system. When Caroline Wiesner, with her colleague Kareem Tebos, at the time Caroline Wiesner was at University of Bristol, organized a workshop that brought together an interdisciplinary group of scientists to think about, what does stability mean to you in your field? What does stability mean in political science? What does stability mean in physics, in mathematics, in machine learning? And how would you think about democracy as a complex system? And what we saw was that if we think about democracy as a complex system, then this notion of democratic backsliding extends itself very well to instability in these complex systems. And through that, you can actually recommend policies of how would you go about to make the system more stable. So this first paper in terms of stability of democracies just talks about how we can think about democracy as a complex system and how the backsliding is in terms of instability in that. And the second paper was a policy paper that now that you have that world view, you can actually use it to make the world better. And Caroline with James Ladyman has a great book, What is a Complex System, that I highly recommend reading. Again, I don't get any money from Caroline or James Ladyman, but I find it's a very useful book because it talks about complex systems in terms of their features and how you measure it. And so at least from a computer science perspective, from a machine learning perspective, it's a very nice book. So the message of the talk really is just looking at machine learning in a narrow way. And for example, just saying, oh, machine learning is being used in these social facing situations like school hirings and jobs and who goes to jail or who gets released from jail, because machine learning algorithms were being used in terms of who gets released from jail during COVID, who gets care, etc. That really this is just all data issue. And it's not just a data issue, right? And so you need to care about where the data came from and how it was collected. You also need to care about the model. You need to care about what's the output of the model, how people interpret it. You should care about the task and what does that prediction task, for example, mean? Where does that prediction task come from? Who has incentives in using your system? Is it for profit? Is it to actually make the world a better place? Is it that, the judge would like to use your system because then he can go play golf faster? Like what are the incentives for using such a system? And that this system is embedded in a bigger society, is embedded in our complex system. And so then you need to care about the feedback, the fact that you have diversity, the fact that you're going to have disorder, and all of that together. And so just popping up from this narrow view of, just my machine learning system, and thinking about, no, my machine learning system is embedded into this complex system, and there's this huge feedback. So on that note, thank you very much, and I'm happy to answer any questions.
Thank you very much, Tina. If anybody has questions, please type them on the chat, and I'll forward them to Tina. Julia Tagüeña asks whether you are in contact with the Stanford group that studies gender dimension. I don't know the name of the group, because she says that they have a methodology that might be useful.
Oh, I am not. I have to look into that. I don't know in terms of I know, for example, folks like Aaron Closet and Dan Larimore at University of Colorado have done some really good work in terms of hiring, and both in terms of like mobility in computer science departments and other departments in the US, like history departments, and also in terms of gender. But I would love to get that reference.
Yeah. I can email it to you.
Thank you. That would be great.
So it's interesting that you're showing with practical cases several limitations of machine learning. I wonder how generalizable this could be in the sense that, let's say, in the broader AI community, there are still some people speaking about artificial general intelligence. However, it seems to me that there might be even some limitations that are related to the limits of formal systems in general, going back to Gödel and Turing. I don't know what would be your take on that, like in the, well, to better phrase the question, do you think artificial intelligence is inherently limited, or it's just a matter of getting enough computational power and enough models, and they will be? I don't know what we expect.
Yeah, no, I think it's an excellent question, and I don't think that it has to do with like getting more powerful computers or getting more data, etc. I think in part. And I will paraphrase Sophia Noble, who just won MacArthur Award Foundation Genius Award, who's at UCLA. You have no business designing technology for society when you don't know society. And that's what's happening, right? People who don't know society are developing technology for society. And then they think that that technology will not affect them, right? But we're all part of the same system and it will affect you, right? And in fact, what I see in this whole AI ethics, fairness, and machine learning space, it's a huge chasm. It's like as big as the Grand Canyon, where on one side, you have folks like Timnit Gebru and folks from the marginalized communities saying, look, these algorithms are being used in our communities and are causing harm. Like, we need to slow down. And then the people from the privileged communities saying, oh, well, we're advancing science, right? And patting themselves on the back. And so it's just completely divided, and it's very upsetting in some sense, right? Because the people who are saying, oh, we're advancing science, they're not being affected and their communities are not being effective. And then people who are all about hype are taking that and making money, doing whatever, and hurting these marginalized people. And so really, if one wants to do AI ethics, if one wants to do fairness and machine learning, it's like going and talking to people and understanding what is going on before like saying, oh, use my algorithm. And so at Northeastern, for example, I'm part of the criminal justice task force. And so, you know, we hear from folks who are in jail, we hear from prosecutors, we hear from judges. And so really knowing what is happening before you design your algorithm is extremely important.
Yes, I guess it's equivalent to engineers designing kitchens when they don't even cook. And it's like,
yeah, actually, that's such a good point, because actually at last year's NeurIPS, actually, my colleague who you know, who has connection to UNAM, I think she actually went to UNAM, Saif Savage, gave a talk at NeurIPS this last year. And at NeurIPS, there was her talk was amazing in terms of future work. And then there was another keynote talk about how, you know, we don't design bridges that only work for white people. Right. No. But effectively what's happening is we're designing systems that are being used that only really work for white people. Right. And like, for example, we saw with the gender shades, right, that these, you know, state of the art commercial facial recognition systems were not doing well on darker skinned people, in particular, darker skinned women. Right.
Yes.
So this is where we are. Yeah, I'm not so worried about the artificial general intelligence. I mean, I'm happy to discuss it, but like in terms of what is happening now in real life, like people are getting harmed. We need to like address that first.
Yes. And AGI is not coming anywhere. So
yeah, I'm not worried about singularity. Yeah.
Great. So Gabriel Ramos Fernandez asks, thanks for the talk. How would a precautionary principle look for preventing decision-making based on machine learning, given challenges you have reviewed?
Yeah, excellent question. And thank you for your kind words. A simple thing that can happen is to tell the decision maker how certain the algorithm is. So as I was saying, in terms of like these pre-trial disposition algorithms, like the Arnold Foundation Public Safety Assessment Tool or North Point's Compass, they just give a number. They don't say like, okay, how certain was the algorithm? You're saying risk of Tina committing a crime is 9, but maybe the algorithm is only 50% sure, right? So none of that is happening. And there are cases in which judges are actually using these algorithms because supposedly the algorithms are objective, right? As if they were expert system, like the expert witnesses, sorry, right? Without cross-examining them. Like, how would you have ruled if Tina was blonde and blue-eyed, right? That does not come about, right? And so there's some of that just like putting some doubt in the decision maker's mind. I think actually, so I guess to end on a positive note, where the algorithms can be used is to show bad policies. Like in New York City, there was this policy of stop and frisk. And anytime you have a policy, there's an intent for that policy. And if you look at the data from that policy being executed and try to reconstruct that intent of the policy, it looks like the policy was to stop Black and brown young people and harass them, right? And so then if you can show, wait a second, there's a disconnect here, you can either change the execution of the policy or you can change the policy. And I think that's where machine learning can be very helpful as opposed to the whole, prediction, recommendation business that's going on now. Because
I guess that biases and prejudices we've always had, and only that by transmitting them into our algorithms, they are becoming more explicit. So hopefully we can address them better.
Yes, and actually, another person which I know your audience or a good chunk of your audience would know is Cesar Hidalgo, right? And he has a book, I highly recommend it. It's free online. It's called How Humans Judge Machines. So if you go to Google and type How Humans Judge Machines, it comes up. And maybe he spoke to you guys, but and he's like, oh, humans judge machines as if machines have no intent, right? So if a machine causes harm, as if the machine had no intent, but a human causes harm to you, the human had intent. Well, where the hell did the machine come from, right? A human designed that machine. And so I really like his work. It addresses how humans judge machines from the psychology, from the crowdsourcing point, and somebody needs to do it from the philosophy, the normative point, but his work is fantastic. I highly recommend that book.
Yes, he gave a talk at the C3 before the pandemic, and he spoke about that. And also Caroline Weissner gave one of the colloquiums. So.
Oh, excellent. Excellent. Yeah, it's a small world.
Yes,
it's a small world.
In that talk, she speaks more about the book, which I also recommend, buy her book.
That's great. Yeah. And I don't think you get anything from people buying his, and I don't get anything, but the book is fantastic.
Buy Cesar's book as well.
Yes. Though Cesar's book is available free online. I mean, especially for students. So,
well, there are congratulations. But
thank you.
Let me check. I think that's all the questions. So thank you again. Tina, it has been a really interesting talk, and hope we'll meet soon in not in the virtual medium.
Yes, indeed. Thank you so much, Carlos, and thank you so much to the center and the audience. And happy holidays to everyone, and best wishes for the new year.
Yeah, thank you to you as well.
Thanks. Bye-bye.